Okay, welcome everybody to the top of page 114 in the workbook. And we're going to do example 1, which is going to be our first example of actually building a Taylor series using the formula that we developed on the previous page. And in this example, we're going to return to the preliminary example that we looked at a few pages ago. And we're going to build the series for that function again using this more systematic process. We're going to see it's a little bit shorter than the way that we did it in the preliminary example. Okay, so just so we don't have to keep flipping back and forth between pages, I went ahead and just copied down the formula for a Taylor series from the previous page. That's what we're being asked to build here. Okay, and we could start by asking ourselves, what do we actually have to do here if we want to use this formula? Well, really, all that we have to calculate are a bunch of derivatives and to substitute in whatever the number a is that they're giving us in the problem. So the good news here is that if you can take derivatives, you can build a Taylor series. That's really all there is to it. All right, so we'll start with our function. We'll take a bunch of derivatives. We kind of already did this calculation in the preliminary example. We'll go out to the fourth derivative here. And then, if you look up at the formula at the top of the page here again for the Taylor series, we need to substitute the number a in to each of the derivatives to get those numbers that we circled in that formula at the top of the page. What is a in our case? Well, they told us a is equal to 0, and we have to know that. That has to be given to us in order to build a Taylor series. So we're just going to take all of these functions and derivatives and just plug 0 in for all of our x's. Okay, and you might remember we did these same calculations back in the preliminary example. So f of 0, for example, we're going to take 0 and substitute it in to e to the 2x. So that's going to give us e to the 0, which is 1. And then f prime of 0 is going to be 2e to the 0, which is 2. And we'd just continue. We get the same list of numbers that we did before. Okay, and then we come to the step where we actually want to build the series. Let's see if we can do that. Okay, well, the formula for the Taylor series is equal to, this formula up at the top of the page, and they told us that a is 0, so I'm just going to rewrite that with 0, substituted in for all of the a's, and x minus a is just going to turn into x. X minus a squared is just x squared, and so on. Okay, and what we need to do, again, is just to fill in these numbers. Okay, we calculated all these derivatives that I'm circling up above, and so we'll fill them in by one by one. So f of 0 is equal to 1. We can see that from our calculation up here. F prime of 0 is 2. Okay, f double prime of 0 is 4, and we just continue. Okay, and what we wrote above would actually be an acceptable answer. So we could leave it like that, or we could do a little simplifying. And I'm going to simplify in this case just to illustrate that these numbers are the same numbers that we got back in the preliminary example. So 2 over 1 factorial is 2. 4 over 2 factorial is 4 over 2, which is 2. 8 over 3 factorial, that's 8/6, which is 4/3. Okay, and then 16 over 24, that's 2/3, and so on. notice that that's exactly the same series that we got back a couple of pages ago on page 112. Okay, so we have answered part A to this question, and part B gets a little bit more into the reason why we would want to calculate a Taylor series. It asks us to use this series to do an approximation. Okay, so let's see if we can work through that together. So part B asks us to use Taylor polynomials to approximate the value of f of 0.1. Okay, and they'd like us to compare our approximations to what our calculator is telling us that f of 0.1 is. All right, so how about if we start by calculating f of 0.1? Remember, that's just saying we want to take 0.1 and plug it into the function e to the 2x. So we'll start there. Okay, and you can double check my calculation here. You are going to get 1.221402, and then the decimals kind of just go on. Okay, so we used a calculator to arrive at that number. And what about these Taylor polynomials? Okay, well, this gives us a chance to just review that notation. Let me just scroll up a little bit here. Okay, so P1, for example, all that means is it's the polynomial that we would get if we go back to our Taylor series up here at the top of the page, and we just write down terms and we stop when we get to the first power of x. So we're just going to take 1 plus 2x. And we're plugging in the number 0.1. So how about if we start there and write P1 of 0.1. So we're going to take 1 plus 2x, again, the terms in our Taylor series up until we get to the first power, and we're just going to plug in 0.1 for that x. Okay, you might be able to do that calculation in your head. That's just going to be 1 plus 0.2 is 1.2. Okay, and then similarly for the second Taylor polynomial, P2, we're going to go back to our series at the top of the page, and this time we're going to go until we get to the second power. That's what the 2 means when we write 2. It's referring to the power here. And we're going to plug 0.1 in for all of those x's. Okay, so we've got one more term this time. And you can double check my calculations. If you add up those three terms, this time you're going to get 1.22. Okay, and then one more time with P3. This time we're going to go up until the third power. Okay, plug in 0.1 for all of those x's. Okay, and if you do that calculation, you can ask your calculator. This time you're going to get 1.22133. Okay, so the answers, let's go ahead and circle those. Okay, this was our calculator's approximation of f of 0.1, and these were the three approximations using the Taylor polynomials. I'm wondering if you might notice anything about how those numbers are behaving, these three. You see how they're getting closer and closer to the calculator's value of f of 0.1. So you can think of these three numbers that we have here as approximations of the number f of 0.1, and they're getting more and more accurate the bigger that n gets. This is how Taylor polynomials behave when a Taylor series converges. Okay, so we'll make one comment just to kind of tie this together. So observe that our approximations get closer to f of 0.1 as n increases. If we took P4, P5, we would just notice that these numbers that are coming out get closer and closer to this f of 0.1 up here that we calculated. Okay, and we'll see the same behavior in future examples that we do.